All right, hi everyone. Let me send you here in the chat. I should be able to send you files soon. Does anyone know how I send the files through here? I can't. Okay, I'll ask Nuriya and Lidia to upload it now. Or maybe I'll do it myself if you give me a minute. Yes, it's a whole process. Turn editing on. And I'll edit here. Settings, and I should be able to send you this new file. Okay, it was a long way around, but it should be now on Moodle, save and return to course. Okay, it should be there. Okay, so while you go fetch it, and please let me know if you don't find it, but maybe I'll just tell you what the lecture is about today. We'll do two parts, and the two parts will be very different, which is a good thing. So in the first part, we will talk about the hydrogen atom, so we'll just wrap up. And mostly now this will be conceptual things like what we can learn from all this maths we've been doing. There'll be one trick that is something we can use in other settings. So this is the wrap up. And that will be we'll see what it is in a moment. Feynman-Hellmann theorem, which can be used. So this will be the first half of the lecture. And then the second half, we go to one of my favorite topics, you'll see that I'll pick up in energy as well. It will be about modeling uncertainty. In quantum mechanics, certainty. And if you're taking the QIT course, the quantum information theory course, then you'll see that there's some overlap now because we'll talk about density matrices. So how do we model uncertainty about the state and about local information? So trace and partial trace. Okay, good. Okay, so let's just recap very quickly what we did last time. So what we've been wrapping up is everything to do with spin and angular momentum, which was the last kind of physical model topic of the course. And now we go more to the information theory. Okay, so we looked at Hamiltonians that had a central potential, so p squared over 2 the mass plus something that depends only on the radius. So on the distance to some center that we chose very cleverly. And then we saw that in these cases, the Hamiltonian commutes with the angular momentum operators. And then we saw that from here, all the energy eigenstates were also angular momentum eigenstates, right? So we saw that if you have for this state, so this is the Schrödinger equation that we saw, and let's say E can depend on two numbers, actually to one dependent n. But then we saw that from here, we saw, well, all these states must have the formula, must have this form, where this was the eigenstate of L2, and this, corresponds to the eigenvalue of Lz and L2, and this depends just on the shape of the Hamiltonian, right? And from here, we saw, well, actually the wave functions corresponding to this state, they are the same as for the angular momentum, so can depend now in this new number n, which gives a degeneracy in angular momentum. Chuk. And we saw this is some radial function, can depend on n and l, and the rest were the spherical harmonics, right, which we saw in previous lectures. Okay. So far with me, and then what we did was to kind of simplify this equation for this kind of states, and I'll just repeat it here just for completeness. Okay, so we said, oh well, we define some auxiliary functions. So we say, well, this will actually simplify a lot if instead of the radial function, we multiply it by r. This is something you'll prove in the tutorial this week. And if we write an effective potential that depends on L and R, is the original potential, L plus 1 over 2 1 over r squared. Then we saw that in these cases, we have, well, this function where r equals 0 is 0, and for r larger than 0, then it's exactly the same Schrödinger equation as for particles in 1D potential, right? This was the big conclusion. Chuk, R2, and then we said, well, you'll show in the tutorial that it simplifies to this, because the part we didn't do before was to simplify this part. So anyway, so we got this. This looks simple, but of course it will depend on the shape of this potential, right? And I told you, look, essentially there's two examples we can solve analytically. One is the hydrogen atom. The other one is a harmonic oscillator, which maybe I'll do this in this extra lecture. And so what was the case of the hydrogen atom? I explain why the Hamiltonian is this. But what matters is that you only have one electron that is much smaller than the atom. So we think, well, the atom is fixed, and the Hilbert space is just the Hilbert space of the electron, right? We think that the proton, the nucleus, is kind of part of the setting. Okay, so then this was the potential varied with 1 over r. Then we also have this part of 1 over r squared, and I told you this can be solved analytically. And I guess what you're all eager to know is if people have asked me to show this explicitly in the lecture, and I'm happy to say they didn't. So we will not show how to solve this and find all the solutions. It's in the book in the section that I told you about, and you can look it up. But then the main conclusions was that in this case, we had that the energy was quantized. And it was given by this k squared A4 over 2 h bar squared, 1 over n squared. And that this number n, it's also restricted, so it's a natural number, and it must always be larger than L. And of course, L has to do with the total angular momentum, so it's always larger than absolute value. So this thing. Okay. So then we will look later at how we can how we can correlate this experimentally, right? So we reach this expression here. We have some complicated expressions for the wave functions. And now, like, how do we relate this to things we can measure in the lab? So we'll talk about this later. But first, I said, we're going to learn a trick that can be used not just in this case, but for any Hamiltonian. So suppose that we want to know, say, the average radius of the atom for a given energy level. So let's say we have a quantity of interest. So suppose I want to know the average radius, and this is for what? For one given eigenstate. So what is this physically? Well, if I think I have my proton here in the middle, and then my electron has an orbital somewhere here, and I want to know kind of what's the average distance between the electron and the proton. So later on, this is used, for example, in solid state physics to know how many atoms I can pack in a given volume. For this, I need to know what's the size of an average atom. And because the protons are all glued together in the nucleus, what this means is like how far these electrons are from the nucleus. So I want to know this. And for this, we're going to learn this trick. So first I make the claim of the trick, and then we'll see how it can be useful to compute this, and then we'll prove it. So here's a trick. It has a name, and I'll just write here the name in case people ask you this. It's good to know what things we've learned. Okay, so the claim is the following. If I have an energy eigenstate, and well, both H and E and the formula for the state, they all depend smoothly. We'll see what this means on some parameter lambda, meaning, for example, that in the expression for the energy, there's some parameters here, not n because n is discrete, but for example, k, En, is continuously differentiable on k. Right, H bar is a bit trickier because so suppose that now we can change this constant H bar to be something else. Of course, it's a physical constant, but ignore this. Then you get a singularity at H bar equals 0. But for k, if we change the electrical constant, which is also universal, but suppose we can change it, then En, is a smooth function of this. So that's all it means. So if we have this kind of situation, then if you do the derivative, so for example, the derivative of this function with respect to this constant k, this is the same as the H. Okay, so there we are. And you think, okay, why is this useful? And I'll give you now first an example of why it's useful in this case to compute the radius, and then we'll prove this in general. And the reason why it's useful is that, we'll see, is that this expression can be simple. This will be something we want to compute. For example, it will reduce to this. And this is a way to relate something simple to something we want to compute without needing the exact expression for this complicated wave function. That's That's going to be the ideal. So, wait a minute. Okay, so now let's do this. So let's apply it first. Example, to compute the average R. And I'll be honest that now we'll sweep some stuff under the carpet and then you fix it in the tutorial, because I just want to give the overview of how one would apply this. So we take this thing to be this electrical constant, okay? So then we have what? The n is this thing I said before, k squared, e4, 2h bar squared, n squared. This depends smoothly on n, on k. Great. And the expression for the Hamiltonian, this is important. So this was p squared 2 mu minus k e squared over r. So here I make the r as the operator because we're talking about the operators, not how it's applied to the wave function. In the tutorial, you'll see better what this is here. Okay. But for now, we leave it as it is. So this also depends smoothly on k. Excellent. And for the expressions for this, well, we would have to see exactly what they are, but I just tell you they depend smoothly on k. We trust. Yeah. Okay. If you're doing this, if you wanted to apply this to some new physical setting, you'd actually have to check this. Okay, so then we're gonna just apply the statement of the theorem to see how it's useful. So we have this, so lambda is k now, equals our energy eigenstate is NLM. And then we have here the h, the k, and LM, right? So on the left, we have the derivative of something easy, which was this minus mu e4k squared 2h bar squared and squared. And on the right, well, it turns out this derivative is also very easy. So we have p squared over 2 mu. Here there's no k, so the derivative of this part is going to be 0. And for the second part, we have minus k e squared over this operator r. And LM. Okay. So we just do the derivatives on both sides. Why is there a minus here? Okay. Good. So we do the derivative on this side. So the derivative of k squared is just 2k. So it cancels out with the k below. So it's minus mu e4 k. Sorry, the 2 canceled out. I just said squared equals. And now what we have here, so we have 0 minus p squared over r. And LM. Okay. So now e squared minus e squared is a constant, so we can come out of this inner product, but we'll leave the operator there. So then we get what? The minus cancel out, the e squared cancels, so we have mu k h bar n squared equals, and now NLM 1 over r NLM. But this is the thing kind of that we were looking for, because this is already the average of this operator that we have here of NLM. Right? So then what you'll do in the tutorial is to relate this to the average of the operator we're looking for. So essentially it's going to be just taking the inverse, but let's define this object properly, and let's like show that this thing follows. That's what you'll do with Lydia this Thursday. So then you get that this is n squared times some constant, 0 constant. Okay. So now what did we observe from here? That the average radius of this hydrogen atom, depending on the energy level, depends with n squared times this constant. This constant here we call A, and this is the Bohr radius. So before people had quantum mechanics, they still tried to make some models for the hydrogen atom that were semi-classical. And if you take QM1, we go through all of them. And they don't get all the things right, of course, that's why we need quantum mechanics. But one of the things they got is this kind of estimation for the average radius. So this is kind of a leftover from pre-quantum mechanics. So then R, so the average size of your atom is n squared times this base radius, right? The radius of the ground state. Okay, and because we have this, we can also simplify the expression for the energy in terms of this. So I'll just write. Let's just write conclusions. So En gets minus E squared over A 1 over n squared. That's just rewriting what we did before. And the average R for a state does not depend on the direction of the angular momentum or the total angular momentum. It just depends on the energy level. Okay, good. And A, let's just write it again, is h bar squared. Okay. So, and maybe I'll just write one more thing that we have not done explicitly, but that the expressions for the radial components naturally should depend on this A, right? Because we just saw that on average they should be A times n squared. So we should see this A popping up here, and they do. So they're given by some normalization constant. This is just a constant, and then R over A. So we want this to be 1, and then E2 minus R over A 1 over N. So you see, if R starts being very different from A, then this thing starts decaying. And then some polynomial, these are called the Laguerre polynomials that have degree n minus L minus 1. And it's also R over A. So like the quantity of interest is not just the radius, but the relation between the radius and the standard Bohr radius. Okay, this is something that comes out if you solve the differential equation that we will not do. We still need to prove this theorem. Eh? So let's prove the theorem first. It's very simple, and then we go back to talking about the hydrogen atom. All right. So proof of TE check equals dH to lambda. So it's very simple. So we just take that, well, E was the average energy by definition, right? Is the average of the Hamiltonian for this eigenstate. So now if we take the derivative of E, then you get 3 terms, right? Because we have here 3 objects and you get 3 terms. So let's write first the middle term because that's the one that needs to stay. So we have E dH d lambda. And then we have the derivative of the first times the other 2 plus the first 2 times the derivative of the last one. So we need to show that this is already the result that we want, right? This is this. So now we just need to show that these terms here sum up to 0. So what we do is just say, well, this is an energy eigenstate, right? So by definition, if I have H psi E, this is E psi E, right? That's just it. So this is just a number times psi E. Oh, and here I put the bracket in the wrong place. Let me just move it. And it's the same here. So this would be psi E. And here would be the complex conjugate, but it's a real number, so it's just E again. So then this whole thing, I did it more neat in the lecture notes if you want to see step by step, but this already gives you an intuition. So then this whole thing, we can put it as what? So it's E times derivative of the first times the second plus E, the first times the derivative of the second. And this is what the trick's going to be, because now I say, well, this is just E times, oh, sorry, d lambda should be here. Okay. So this whole thing is just E d lambda of this inner product, right? Because it's just like the rule for derivative of a product. So if I have the derivative of this, it's going to be derivative of the first times the second plus the first times derivative of the second, right? So I can simplify to this. So it's derivative in order to lambda of this thing. But this is a normalized state, which means that this here is 1. And 1 does not depend on lambda, it's just 1, it's a constant, right? So then this whole thing must be 0. And that's the proof. Okay, so we saw this as 3 terms, and we saw that the other 2 terms can be rewritten as the derivative of a constant, and that's 0. So that's the proof of the theorem. Good. So with that out of the way, now we can talk about the hydrogen atom again. So why have we been talking about so much is because it's kind of a big deal. So let me tell you about how one tests this in the lab. So and the main thing that was available in the in the beginning of the 20th century is spectroscopy experiments, which are becoming more and more refined. But the main idea is the following. So suppose you have like two energy levels, and your electron, say, is on the upper level. Then they want to tend to relax, meaning to go to the ground levels, right? So you have here En, and you have here En prime. And so maybe there's more, and they'll go in small steps, one by one by one. Or maybe they jump. There's special rules as well that come come up a lot in later courses of quantum mechanics of how far down they relax. But one of the things is that, well, if they go down, and in physics we have conservation of energy, then this energy must go somewhere. And so and the idea is that, well, then they must emit a photon, and this photon has the energy that corresponds to the difference between these two levels, right? So then we have the energy of the photon is the energy of n minus energy of, right? So that overall energy is conserved. And we can already write this in terms for the hydrogen atom, it's this, right? Because there was a minus sign, I put this one first, -1 over. So it's n prime squared minus n squared, okay? And what is the energy of a photon? It's related to the frequency, which means the color of the photon, essentially. So energy of a photon is the frequency, and the formula is this, that it's actually h bar times the frequency. And what's the frequency? We don't observe the frequency directly, but the frequency is, this was a nu, and this is a v for the speed of the electron, of the photon, sorry, over, this is the wavelength. So this is, I'll write it down. And this is the color, essentially, of the photon. So, for example, if you do this in vacuum, then this is the speed of light, and there's the thing that you detect. And then you can compare this to that. So from the spectrum, so essentially, you take a bunch of hydrogen atoms. You need to give them energy so that they get excited. So, for example, you can just shine. White light is a mixture of all wavelengths. So they'll get something, and then you turn off the lights, and you see what colors they emit. So what colors they shine with, and then you get a spectrum that might look. I'll show you exactly what it looks like, but for example. Something like this, right? And you know that each of these lines will correspond to one of these energy gaps. So then we can actually compare very well to the theory if, you know, if they correspond to the energy eigenvalues that you computed. So let's go have a look. You can stop sharing here. And I'll share my other screen. So I had it open here. Yeah, so this would be for the one of the emission spectrums for the hydrogen. So it's very neat, right? Only a few lines there. So you have the wavelength in the horizontal axis. If you look at iron, this is atomic level, I think 26, something like this, very big. So now you have a bunch of electrons and lots of interactions between them. So of course, many more energy levels, right? And then this can be computed. I mean, this, you would not compute them analytically, of course. Yeah, 26. But where it is, there it is. Oh, so there we are. We can see them here. So, so n equals 1, this smallest circle, this corresponds to the ground state. And then all of these lines that corresponds to different wavelengths is what's the decay if the electron is, for example, here on n equals 4 and decays down to n equal 1. then this is the wavelength of the electron, and so on. So they have different names depending on what is like the end state, and so on. And these things can be computed, and then you can use this as to check your theory, right? Okay. Now these are very annoying computations, but someone needs to do them to see if quantum mechanics is the right theory. Okay. So this was for the hydrogen atom, which I said is the simplest thing. So what if you have other atoms? So what's the problem then? So well, the problem is that then if an atom is neutral, then just a moment. Daqui a 10 minutes? Okay. Right. Okay. So if the atom is neutral, then the number of protons is the sum of the number of electrons, and this is a problem. So this is Z is the atomic number. Why is it a problem? Because, well, then we have to take into account all the interactions between the electrons. For example, if Z equals 2, then, not only are they attracted to the nucleus, but they also repelled by each other. And you cannot make this approximation anyway that, one electron is just much heavier than the other, so we just consider it part of the scenario. We cannot do this, right? So then you have to say, well, we have the one for R1 attracted to the nucleus, then the second electron is also attracted to the nucleus, and then we even have some interaction between them, which depends on the distance between them. And then there's even a few more factors because they have fermions, there's some extra rules, it's complicated. Right? But there's something we can do in the lab, which is, okay, the problem is not the number of protons, the problem is just the number of electrons. So just get rid of the other electrons. So this is something that can be done for some atoms. You can just ionize them, meaning you're left with only one electron. Okay, so in these calculations we can do, because the main difference there is that then R of R is that, sorry, I'm missing the K here, K. The main difference then is that you get this constant Z here, because the sum of the product of the two charges is now 2 times the, so this is the nucleus, 2 protons times your electron outside. Right? So one can do this for some simple atoms like helium, for example, and then it's very similar solutions to the hydrogen atom up to some numbers, right? For more complicated things, we just cannot solve this analytically, so we get into the territory of computational physics and all these numerical solutions. And like we saw before, like in the case of hydrogen atoms, there's lots of little tricks we saw that we use to simplify our lives. This is also true if we use computers, right? Lots of little tricks. But actually, even for the hydrogen atom, the story is not so simple. So if we did spectroscopy now more carefully, and we can get more and more resolution between different wavelengths, we see that we don't get this perfect lines, but actually they can split a bit. And then if you, for example, act with the magnetic field, then they split even more. And this is something that's used, for example, in trapped ion quantum computing. So because what kind of things have we been neglecting in our consideration? And we will not go through any details of any of them, but it's just to give you an idea of how we do this. So first of all, we spent a lot of time saying that the electron has a spin and spin on one half particle, right? But we've not considered this at all so far. We just considered the orbital degree of freedom of the electron. So we have the internal spin. Which turns out it interacts with the orbital degree of freedom. So we get something that, well, I'll tell you a little bit. And also, if you plug in a magnetic field, if you turn on a magnetic field, then it also interacts with that and changes everything. Then we also have actually the internal spin of the proton, which we've not talked about at all. So this will give a very, very, very fine splitting in the energy levels. And turns out, that even if you consider those two, and you draw some Hamiltonians that are kind of how classically you think of, if you think of the spin as a little magnet interacting with the current caused by the electron being moving, you do some, you get some Hamiltonian, you do all the calculations, and turns out that everything at the end is wrong by a factor of 1/2. And the reason for this is that turns out you need to take special relativity into consideration into this. So there's relativity corrections, which is funny, right? Because I don't know if you had any course with special relativity, but normally we're used to it only mattering when we have objects moving very fast, very close to the speed of light, and we think of like a spaceship going away. And it turns out that it matches even for like the smallest things, even for atoms. Discover this was by doing the classical calculation with quantum mechanics, but classically inspired Hamiltonian, and seeing that we get the wrong results, so we need to correct this. So let's just talk a little bit about this part, because it's nice if you see it again in QM2, or if you do some physics later on. It's nice because it's the kind of tools we've been talking about before. So the whole Hilbert space of the electron, it's going to be the Hilbert space of the position, right? 3D, and the Hilbert space of the spin. So this is spin 1/2, right? That we talked about. And we said, well, here we have angular momentum is a kind of spin. So this is a kind of spin system. This is a kind of spin system. We have the tensor product of two spin systems. So we have the machinery to do this. This is just essentially adding spins. Now, one needs a lot of representation theory and so on to actually find a nice decomposition into subspaces of this, because the angular momentum is a bit trickier than the other spins we've talked about. But this means that we can have, for any thing of the electron, any state of the electron, we can always decompose it in a basis that depends on what? Well, depends on n, L, M, and now it also has the internal spin, right? So M of the spin, MS. There'll be some coefficients that depends on all these things, L and MS, and LM. This form a basis times MS. So this is in the 3D and this is in the spin. Okay. And now all of these numbers, they are limited, right? So n can go from 1 to plus infinity. L can only go up to n minus 1, we saw. M can go from minus L to plus L, and MS can go to minus 1/2. 1/2 because it's a spin 1/2. Right? Okay. And now, using all the spin machinery, what we do is to take this, what people do is to take this and then rewrite this, find a new global basis right? Where they find some new quantum numbers. So this corresponds to the total spin, which, well, that's right. I think even if you look at, depending on the year on who's teaching QM1, you might do this explicitly. So if you look at scripts of QM1, you might find this explicit calculation, right? But just to say, this is the same as you did in the tutorials as when I have two spin-1 particles, and now I want to see all the global states and express them in this, in terms of subspaces of the global space. So it's the same machinery, but can be applied here in this more complicated case. And then you have the total Hamiltonian, which is, I just say, well, we have, I'll let you go for a break in a minute. Let me just write down. So we have this H3D. This is what we saw before, the normal Hamiltonian of the electron, of the position degree of freedom with the momentum, so on. Then we have some interaction. Between the two, and this depends on L times S over R2, 3, something like this. And this is where you need to put relativistic constraints. And then, if you have a magnetic field on top of this, you can also add some agent spin of this magnetic field, which will be what some constant. This is the strength of the magnetic field. Then, depending on the direction of the magnetic field, you can have here X, Y, Z. Yeah. Looks terribly complicated, right? So what people do in practice, for example, in a Entropy lab, is to then take a magnetic field and increase it so that you can kind of take one energy level and split it into this plus spin 1/2 and spin minus 1/2. And then we can say, oh, maybe this is a qubit I can use, or maybe I can find some other subsystems that can be used, for example, as qubits. There's just, I just want to tell you what all these corrections look like in the end. So I'll just draw this diagram, and then we can go for a break. So let's say, for example, just the first two energy levels. So here's just the total energy. So we saw that there's these two. Of course, here you can have many values. You can have two different values for L, yes, and you can different values for M, and so on. Now, if we take into consideration also the spin of the electron, you get what is called the fine structure. And this is even without a magnetic field, an external magnetic field. So this one splits into two, and this correspond to this subspaces. Right, I told you here that, how can we write this in terms of a new quantum number? That's J, that is a subspace of the combined spin. Now, if you take now into account even more this possible spins of the protons in the nucleus, then just for the hydrogen atom, each of them gets split into two, because again, the proton can be spin up or spin down. Right? And this will have some different effect on the atom. Okay, and so on. And this is called the hyperfine structure. Okay. So, and I'm not sure what parts of this can be done analytically, but I don't want to say sanity, but it makes sense to ask a computer to solve these differential equations as soon as you start considering more variables, because it just gets very complicated. But this to say, so from basic quantum mechanics, we developed all this understanding of spin, and then we say, well, we apply it to the hydrogen atom, and we see, yes, we check, we do see these things in the lab in terms of this, the energy of the photons that are emitted. And then we look a bit closer and say, oh, wait a moment, there's actually some splitting here. This can be explained by the spin of the electron plus relativistic corrections. And then you look even closer, and there's actually even more options for each of them. And these gaps get smaller and smaller. And this can be explained due to the spin of the proton, and so on. So there's always more complexity to be found. Yeah, but it's still all within the same theory, which is quantum mechanics plus special relativity, which is still treatable. Okay, so we go for a break here. Let's start at 20 past, and we start with a new topic. Okay, welcome back. I think the new lecture notes should be now on Moodle. Managed to scan them. Let's continue this. Okay. Can you hear me, or is there too much background noise? Okay, if you still can hear me clearly, if there's too much noise at some point, please just write in the chat. Okay, perfect. Thank you. Okay, so now we go into a new topic, and hopefully we can spend the rest of the course exploring this. And this is about modeling uncertainty. Okay, so so far we did everything with the Schrödinger equation and so on, but turns out the Schrödinger equation is kind of a luxury that we can apply if we know exactly the initial state and you know exactly the Hamiltonian. And in practice, this is very, very seldom the case, right? There's a lot of noise, for example, in the experiment, and we know that we can create approximately a state, but never, ever appear. We never know exactly the state. This is impossible. There's just too much noise, too much interaction with the environment, even in the best cases. So, okay, so we will talk about a general way to model uncertainty, which you might have seen if you took QIT, and then we'll see later in the next few classes how to apply this to the physics problems that we were studying. Okay. So now let me give you just a toy setting. Okay. So suppose that you have a machine that gives you a quantum state, or maybe it's your friend or someone. And all you know about this is that with some probability, with probability pi, it is a state psi i. And then what can you do to this state? Well, you can do all the things, right? You're just given the system, and you can, for example, apply some evolution, and then you can, for example, measure it. And this could be, is like, turn it off. That's my, sorry. Someone turned on my headphones somehow. Okay, so, turn it off here just please. Okay, good. So now we have this setting, and now what we want is a mathematical model for this setting, which should do what? Like, well, it should give us the right prediction. So we want to find goal. The goal is to find a model that, one, it's correct, meaning that it's compatible with the correct predictions of, what happens when I do here, what are the probabilities of getting different outcomes, no matter what the unitary is. And I mean, it should also be, it should not be very cumbersome. We want it to be an object as easy to maneuver as possible. So we want it to be kind of compact mathematically. This is a very subjective notion. It just means a nice object to handle it. So let's just call this setting star. And at the moment, we can just describe it, well, with some probability, we get the state psi I, right? This is my setting. And I'm looking for a way to model this. So to do this, first, we're just going to see what happens, what are the probabilities of getting the different outcomes here. Okay. So, and for now, let's consider even the case where we don't have a unitary there. We take whatever this machine gives us and we measure it. So we take a projective measurement, right? Pi k. We have some Hilbert space H. Yeah. So what's the what's the probability of getting outcome K in the setting, I call this setting star. Well, it's the probability of having that the machine gave me state psi I, and then for each of the states, it's going to be the probability of getting K, or that state according to quantum mechanics, right? So this is the quantum mechanics part, and this is my probabilistic knowledge modeling part. Okay, so this is PI. And then this probability from quantum mechanics, we know that it's psi I, okay, right? This is the Born rule. So what we'll do is to rewrite this. And we'll do this because later on, this will allow us to find an object that is very compact to describe the whole situation. So for this, I need to introduce a new operator. So let me introduce you the trace operator. And this is, it's written like this. You apply this to any matrix, or in an operator if you are in continuous variables, it doesn't matter. And this is sum over J, J, A, J, where these J's are some orthonormal bases. Of what? Of your Hilbert space, where A is an operator. A linear operator. Okay? So if you want to look at it visually, so this is A as a matrix, and the trace is really just summing all the diagonal elements. And J could be any basis. So in the tutorial, you'll see that there are some properties. Namely, it's linear, meaning if I have trace of alpha A plus beta B, alpha trace of A plus beta trace of B. It's cyclic. This is a fun property that's very, very useful. Trace of ABC, meaning that if I move this A to the other side, it doesn't change anything. So this is the same as trace of BCA. You'll prove this tutorial. And the last thing, it's a special case of that, is that its space is independent, meaning that I can choose any basis J here. So in practice, mathematically, what this means is that if I apply some unitary, before and after the operator, then this gives me, again, the trace of A. For U unitary, right? Because one way to see it is that you just put the U here and the U there, U dagger there, and this gives you a new basis, right? This gives you a new basis. Okay. So this you'll prove all in the tutorial. We need this because now we're just going to rewrite this. We want to write this thing as a trace because it will be useful later. So what we do is we just choose a basis where, so let's say by 0, by 1, 2, 2. This is the discrete case is exactly the same, where we just choose a basis such that phi 0 is this, and because it's orthonormal, this in particular means that phi I, phi A, F, sorry, J, let's call this J. this is going to be 0 for all the others, right? So I said J 0. Okay, why am I doing this? Because then I can say, well, what is the trace of any operator, for example, pk, and now I put here my phi I. Well, I'm just going to write this as the sum J phi J, and now this thing that was in the middle, so I can. Let me just change color. Okay. I, and now come again the J. Okay, so this is just a definition of trace. I'll go back so I can show you. This is just a definition of trace. I chose this special basis J such that my state of interest, this one, is going to be one of the elements. And this is nice because now this gives me, well, this is an inner product and this is G0. And here I know that for the only surviving terms, this is going to be my state of interest. So then this whole thing is just say I pi k. And that's the probability of getting k with, okay. Why did I do all this? Because now I can go back and we want to look at the probability. Wait, where were we? We were looking here at this probability of getting k for my state, for my setting star. So let's just copy this and come back. And what we gained is that now we can use all these properties of the trace. Right, so we rewrote this as sum I forgot the sum I, sorry. Okay, good. So now we can write all of this again. Sum I, pi, and now trace of pi k I. And now the nice thing here is that now we can use the properties of the trace. Say the trace is linear. So I say, well, then this is just a trace of say I, pi, the projector. And now here comes my state. And now I can even simplify this further because this projector does not depend on I, so it can come out here. This has nothing to do with the trace, just coming out of a sum because it's a constant. Just like k, and now we have this thing here. Now this thing here is a matrix, right? This object here is a matrix because this is a matrix element with this value. So this whole thing is a matrix. This is another matrix. And this is what we call rho. It's what we call the density matrix. So let me just write here what we got. We got that this is trace of pi k times rho. And I'll write here. So rho sum of I also works in the continuous case, exactly the same. It could also be if I have a machine that gives me some density of probability, I can have need a new Greek letter. Right. In the continuous case, it also works, and that's where the name comes from. So it comes from density of probability, nothing to do with like density as in volume density. It's an unfortunate name, because in most discrete cases we don't look at it and think it's a density, but that's where it comes from. Okay, so now this is our candidate object to model our setting, and the main result is that the probabilities of getting some outcome k in this setting is a trace of projector times this matrix. Okay, good. But now what about evolutions? We said maybe I want to apply first an evolution and then measure it, right? And then we need to see that, well, how do I evolve this object in time, or how do I evolve it according to some unitary, right? So now, again, we have now the machine producing states, and now I'm going to apply some unitary, and then I'm going to measure it. So what is happening here? Well, first, each of these phi i's would evolve to u phi I. And how do we evolve the density matrix? We don't know yet. But so what we'll do is now look at what happens to these probabilities here. Okay. And this will allow us to find the right object. Very good. So we look at them. So after the evolution, what we have, well, the probability of getting outcome k is now, well, let's just call this say prime I. Okay, so then this is I, pi, probability of getting outcome k for each of these states psi I prime, right? And this, okay, we'll just do it. Summit I, pi, and now here comes trace. This is one way to do it. You can also try to use the density matrix directly here. Let's not do it. Let's do it properly. So psi I prime. Good. And now, of course, we can, because the trace is linear, we can put this probability inside. And because the pi k does not depend on anything, we just put it here. Now here it goes. Psi I, pi I. Okay. This already looks like a density matrix. And now we just replace what these psi i's are. Sum over I, pi. And now this was the unitary applied to my original state. And here's the same, but because it's the brown of the cat, I need to put the dagger. Okay. And now, because it's unitaries, they don't depend on the I, they can come out outside the sum. So then I just bring them out and I say, okay. So then it's a trace of pi k, and now u, this sum, and now u dagger. But this was my original density matrix, right? So then this whole thing is just trace of pi k, u rho, u dagger. And this is my this is my evolved density matrix. So then what's the conclusion? I'll write here local, because we have only one subsystem and we're talking about local evolution of this subsystem. Rho goes to u rho u dagger. Okay. So now we have this object which can be used to model any setting of this form, right? Doesn't matter what the origin of this probability distribution is. If locally all I know is that I get some states with some probabilities, then I can always model it like this. So let me let me give you some examples. And of course, we're going to look at the simplest possible setting, qubit, only 2 possible states. And these examples are kind of special. So suppose that my machine gives me either state 0 or 1 with probability 1/2. Well, then rho is what? It's going to be 1/2 of 0, 0 plus 1/2 of 1, 1. But not 0, 0 plus 1, 1 is just the identity matrix, which we've seen before. So this is just the identity matrix divided by 2. In matrix form, it looks like this. So it just has the diagram. Now let's look at a completely different situation. So I bought this machine. All I know is that it gives in state 0 or 1 with probability 1/2. And now I buy there's a second machine. It looks the same from the outside, but in fact, it has a very different behavior. It gives me states plus or minus with probability 1/2 too. Well, then in this case, so we have 1/2 of plus plus 1/2 of minus minus. And what's the problem here is that this is also the identity matrix. We've done, I mean, you can do this explicitly, but you can just think, well, it's expanding in one basis with the same coefficients. You can do it explicitly and see that, well, this is in fact the same matrix. And what does it mean that it's the same matrix? It means that, well, then we cannot, if I'm either in this situation 1 or in this situation 2, I'm giving one of the 2 machines and I'm told, well, try to guess which one it is. I cannot guess with probability based than guessing at random, right? Because this object here is sufficient to compute all the probabilities of all experiments I can perform on this one qubit. And it's the same object as that one. So no matter what evolution I do and what measurements I do at the end, as long as they're only on this one qubit, then I cannot distinguish these 2 situations physically. That's a very funny concept because we know from the outside that they are very different situations, right? But there's this strange kind of compression of degeneracy that tells me I cannot distinguish these 2. So we will see some more properties of this kind of objects. Well, in fact, you'll see them in the tutorial. So let me tell you more special cases. So and we'll explore this idea of like I cannot distinguish these 2 things. So let me tell about more special cases. So if I buy the best possible machine, it's a machine that reliably produces always the same states, right? So the probability is 1 for one state and 0 for all the others. So this is rho equals check, check. So this is the I for which the probability is 1, all the others are 0. This is what we called a pure state. And this is the state of maximal information. So everything we've been doing in the lecture so far was always pure states. Because when you look at the dynamics of this, it's just you check, check, you dagger, there's no sum. So in practice, we can always work with just this object, with just the vector. We don't need to consider the matrix for most things. Okay? We'll see later this explicitly. So everything we've done so far is this. Okay? So keep in mind that everything we've done so far corresponds to knowing exactly what quantum state we have in front of us. And we'll see later why this is not possible in practice. In the other extreme, it's something like this, right? It's maximum ignorance. And this corresponds to the case where, well, what I have is kind of just the identity matrix divided by the dimension of my Hilbert space. meaning it could be any of these states with the same probability. I know nothing. This is what is called a fully mixed state. Of course, there are many possibilities in between for different probability distributions. And then we can try to quantify how much information we know about this, right? Now, there's many measures to quantify this, and this is important. We'll repeat this later. Each measure is only relevant if it's relevant for some experiment, for some setting, or to quantify something we care about. So one measure that people use a lot is von Neumann entropy. If you've done some classical information theory, this is just a quantum generalization of the Shannon entropy. And you study them in the QIT course, so let me just give an example. So let me tell. So you'll see in the tutorial that you can always expand rho in what is called, let me call here X, in this form. So rho in general, we call these mixed states. Every state that is not pure, we call them mixed, where this is a probability distribution. So even if I don't give you that exact initial setting, you can always reduce it down to, you can always find a diagonal basis. This is called the spectral decomposition. And then there's like entropy measures. And if you just have one quantum system, then they're very simple. Then when you talk about the entropy of some density matrix, it's just the entropy of this probability distribution. So for example, the von Neumann entropy is minus sum over X. So if this is not familiar to you, don't worry. We'll come back to this later, maybe. If this kind of object is familiar to you, it's because it's the Shannon entropy of this probability distribution, right? Just to find the right probability distribution, we need to take this matrix and diagonalize it. So we get this. And this can also be written in operator form as trace of rho. So for pure states, this thing is 0. And for fully mixed states, its maximal is log of the dimension. Okay. This was all to say that if you want to quantify how much information you have about the state, what we do is kind of diagonalize it and then apply information measures in here. It gets much more interesting if you have more than one system. We'll talk about this later. Okay. So there's just one more thing I should definitely cover today because you need it for the tutorial. And this is what happens if your ignorance is something to do with locality. So ignorance about local information. And that's the partial trace. So what's the idea? So suppose you have some rho AB. This belongs to the set of matrices, endomorphisms, linear maps, all the same, of two Hilbert systems. So suppose you have Alice and Bob. Okay, and they share this state. So for example, it could be 2 qubits and Alice has 1 qubit and Bob has a second qubit, right? And what we want to know is if Alice can only see her qubit, can only do measurements in her qubit, how can she model her local information, right? So Alice does not have access to Bob's part. So what is Alice's knowledge? Which means that we're looking for a map that will go from rho AB to give me just some rho A. So it will go from the state of, from the space of maps on the global Hilbert space to book. Just here. I'm looking for something, for some operator that from the global stage, I can describe just Alice's knowledge. Alice's knowledge should be able, we should be able to describe it as a density operator. You'll prove in the tutorial that it is a density operator, okay? So how do we find this? So let's think again that Alice, what Alice can do here, let's suppose that Alice can just measure something with some operator, some measurement, projective measurement pk, right? What's happening in Bob's side? For now, we say nothing is happening in Bob's side. So Alice's measurement, and we already talked a long time ago. How do we model this? So she has her operators p pi k, I put the k there, on her system A, and globally we can look at them like this, right? Like nothing happening on Bob's side. Okay. So now we have a probability of getting k for this joint center rho B, and we want to express this as something happening on a density operator just on Alice's side. Okay, so then what is this? This is a trace of pi k A tensor identity on B times this rho B. This is something we saw before. And now the solution to do this is to expand this trace explicitly. And now let's just take a special case. And the general case, I'll tell you later how you do it. So let's just say that pKa is just like a perfect measurement into like one basis element. So let's suppose we do it like this. So then, well, the trace is a sum over something on the first system, something in the second system. And let's just say in the first system, okay. So of what all the basis elements, J, this is in A, this is in B. Now comes this monster thing, the operator I'm trying to do. Rho B, and now comes again my A. Okay. Now, again, we use this trick that we are free to choose this basis here, right? And now I'm saying now for this special case, we choose the state where we choose the same basis as this basis here. The general case we'll see later. So choose okay. So we choose this basis, which means that, well, in particular, we know that then if you have I pi k, sorry, pi k, this is I k k, and now this here, because they are in the same basis, is just delta ik, right? So it's delta ikk. Okay, so we choose this because then what we had this sum over I, sum over j, and now we have here this acts on the first, this acts on the second. So we have here I'll just write this operator here, k is k directly, tensor j acting on the identity, rho b, I, j. So we have this, and now here, because we chose this basis cleverly, this is delta ik. Okay, right. So we can get rid of one of the sums. Okay. So then we have sum over J. What survived? So here we have still the K. Here we have the J. Rho AB. K. J. Good. And now what we do is to apply another trick. So tricks go here. Well, if I say I have K tensor J, this is the same as having K tensor D identity times identity tensor J. Why do I do this? Because then I can take the K outside of the sum. So this is what? This is K tensor identity. Sorry, the K should be, no, that's right, that's right. And now comes here the sum over J, identity tensor J, rho B, and now here, identity tensor J, and now here comes K tensor identity. Okay, all right. Let's put this whole sum inside brackets. And now let's look at what dimensions we have here. So it looks a bit tricky, but this belongs in the whole space AB. But then we're kind of contracting it because we're acting with it. We're making this inner product in one of the subsystems. So what will survive here is going to be just a state in just row A, which means that in particular, we don't need this identity here because what's left is just on row A. Okay. It's just on HA. Okay, okay, good. So this whole thing is going to belong to the maps just on HA. And then we act with it, with this thing, with this extra bracket. So at the end of the day, we're going to end up with a number, which makes sense because we're looking for a number, right? So and the other nice thing is that this object here does not depend on K, which is our measurement projector. It just depends on the initial state. Right? It just depends on the initial state, and this is just any basis choice. So we call this object here rho A. And what does this give us? Well, this gives us that the probability of getting K with rho B is just K rho A. Okay, and this can be rewritten trace of K rho A. You can see you apply the same trick again, which is trace of IK rho A. So this is what we're looking for. And rho A is this sum over J of identity in A, J, rho B, identity in A. This is the definition. So this is what we call the partial trace over B, meaning partial, every time you talk trace, think of it as just forgetting some information. So we're ignoring all the information on B, tracing out, ignoring all the information on B for some state, from some global state rho B. So this is how we're going to end. And then next time we'll talk more about the properties of this state. But so let's just recap what we did. We wanted to model uncertainty about the state. We saw we can model this as a density operator, and we saw this is the only object needed to compute all the probabilities of all experiments we can compute. Right? In particular, it means that now there are settings that are physically different that we cannot distinguish locally. And then to explore more this idea of locality, we saw, now let's take a global state. Okay, how do we model local knowledge? So knowledge of someone who has access to some subpart. And we have this candidate object, rho A, given by the partial trace over B, which was given like this. So in the tutorial, we'll explore this a bit, and then we'll talk more about other properties of this object here. Then the next step will be, okay, what if we don't know, what do we have uncertainty, not just about the state, but also about the evolution that's happening there? What do we do then? And this will turn out to be very, very useful for lots of physical situations. Okay, so with this, I thank you for your attention, wish you happy lunch, and see you again on Thursday. And if you have questions, I'm here as usual.